Okay, good evening, everybody, and welcome to the last lecture of the semester. I hope you guys are clapping because you've enjoyed the semester, right? Okay. Yeah. So this is the last official lecture for the semester, and for this session we are going to finish our discussion on the chemistry of amines. When we left the last time, we actually finished most of the topics in chapter 24. So at this point, we are going to finish up on this chapter. Essentially, we have only a few reactions to cover, which is the Hoffman elimination, and then of course we will show you examples of heterocycles. But before we do this, let me, as usual, make a few announcements. For those graduating seniors, your final exam is tomorrow, that is Wednesday, April 24 at 6 p.m. In room G8 of the chemistry building. And then for the same graduating seniors, you come back on Thursday, April 25, to join the rest of the class to take exam number 4. Okay, after you finish taking exam number 4, I will compute your grade. That is for the graduating seniors, and I will forward your grade to the registrar before I leave my office on Thursday. That is April 25. And okay, now also for the rest of you, I also want to let you know that we are going to have our last online review session on Sunday. That is Sunday, April 28th at 8 p.m. We are going to have an online review session. And for that session, we are going to review for the final exam and also the ACS exam. By the way, the ACS exam is scheduled for Tuesday, April 30 at 7 p.m. You come into this lecture hall to take that exam. It goes from 7 p.m. to 9 p.m. That is on Tuesday, April 30. Then on Thursday, May the 2nd, we have our final exam for the course. That is also going to be in this room, and that will be May the 2nd. We start the exam at 5 p.m. Keep that in mind. It's not 6 p.m. The exam starts at 5 p.m. It goes from 5 p.m. to 7 p.m. Make sure you make a record of all of this. And finally, the homework assignment for this week, which is our chapter 24, end of chapter 24 questions. This will be due on Sunday, April 28th. Okay? And that is, of course, the last our assignment for the semester. Okay, so at this point, let us go over the problems that you guys have just done in the quiz that you just taken before we finish the chapter 24. Okay, do you want us to go over this? Yes. Okay. Okay, let us see here. Chandler, can you go ahead and read this for us?
Starting from carbonyl acid, show how to synthesize NHN.
Okay, thank you. Okay, so what this question is asking you to do here, starting from propanoic acid, which is this molecule here, You are told to give a synthetic design for this molecule. N-dimethyl butylamine it is this here. In other words, we want to go from propanoic acid to N-dimethyl butylamine. Okay, before we start with this synthetic design, let me ask you a few questions here. If you take a look at the starting material, how many carbon atoms do we have in the starting material? 3. Okay, how about in the product? 4. So therefore, what do we need to do? We need to extend the carbon chain by 1. Okay, so that definitely we need to look for those reactions that will allow you to extend the carbon chain by 1. Okay, by now all of you should have a set of reactions that you can use to do that. And also we see here we need to make a tertiary amine, right? Okay. Okay, so now let us see how do we do that. Let us start. I need your help to do this. Let's start with this here. So what is the first thing you want to do with propanoic acid?
LAH.
What's the first thing you want to do?
LAH.
You want to do LAH reduction?
Yeah.
Okay, so you want to reduce this to the
Alcohol.
primary alcohol. Very good, very good. Okay. So step 1, we want to reduce the acid to the primary alcohol using LAH followed by hydronium ion. Okay, what other reagent can we use to do the same? What other reagent can we use? Or we could also use step 1 borane, step 2 followed by hydronium ion. Okay, these 2 reagents will convert a carboxylic acid to a primary alcohol. Okay, now we got our primary alcohol. What do we know to do now?
PBR3.
Okay, PBR3. We want to transform the primary alcohol to primary alkyl bromide. Okay. PBR3. Now we form the bromide. Now what is the next step?
Green.
You want to form a grignard?
Yeah.
Why do you want to form a grignard?
Because you can do CO2.
Okay, because you want to extend the carbon chain by 1?
Yeah.
Okay, very good. Okay, so let us say step 1, we form a grignard. Okay, let us say some time here. What to be step 2?
CO2.
Okay, you want to add carbon dioxide. Okay, by step 3, hydronium ion. Okay. Okay, so that will give us this here. So at this point, you are going to form another carboxylic acid. In this case, we have extended the carbon chain by 1. Okay, now what do we want to do now?
DCC.
We want to do thionyl chloride
What about DCC?
to do what?
Yeah, to make that Mason use DCC.
Or you want to make the amine?
Yeah, the amide.
You want to make the amide? Okay. Oh yeah, there are 2 methods that we could use. Okay, let us see here. We could go by the Abraham. We could. I'll come back to yours. We could do the thionyl chloride. because you want to make the tertiary amide, right? And that gives you this. And then what do you do after that? You want to use a secondary amine, okay? Okay, so you want to use a secondary amine. This is one of those nucleophilic acid substitution reaction. Okay, so you want to use this. Secondary amine, okay? And that will give us this. Okay, and then after that, what do you do? Then you do LAH reduction. Okay, very good. So you reduce the tertiary amide with LAH, followed by hydronium ion. Like this is here. Oh, sorry. Because the carbonyl will be reduced to a CH2. Now you have your nitrogen there. So we notice here, the LAH will reduce the carbonyl to a CH2, which is what we have here. Okay, so that is one method we could use. Okay, now let us use Lorenzo, let us use your method. Say we could use DCC to make the amide. Okay, so here you could also use DCC and then your amine, right? Your secondary amine. And that will give you the amide. Directly. So you get a chance to say one step. And of course, once you form your amide, that is the same amide as here, as right here. And then all you then do is do your LAH, right? Very good. Okay? Very good. Is there any question on this? Hopefully this is a review for all of you. Let's go to the next question. Okay, Lorna, can you go ahead and read this first? Okay, thank you. So what do we need to do here? Starting from toluene, which is this molecule here. we are told to give a synthetic scheme for this product. P-hydroxyphenyl acetic acid, that is your p-hydroxyphenyl acetic acid. Okay? Okay, if you do the analysis of this problem here, we see here, if we assume that this carbon here will be this carbon, right? So what that tells us, we need to introduce the hydroxy group in the para position. Okay? What reagent do we know that will introduce an hydroxy group to a benzene molecule? What reagent do you know?
It's a process.
A series of reagents, okay. Yeah, what is it? That's okay, exactly. Diazotization, diazonium ion. So at this point, right away, that is a clue that you need to do diazotization. In other words, you have to form a diazonium ion. Once you know that, then the problem is solved. But if you don't know that, you can't do this. Okay, so we know down the road we need, as part of the synthetic design, to incorporate nitrogen into this molecule and then subsequently do a diazotization reaction. Okay, but before we do that, we also know that we need to form a new carbon-carbon bond. By now, you guys know all of the different reagents that you can use to do that. Okay, so let us start with forming the new carbon-carbon bond, and then form the carboxylic acid, and then we'll come back to the diazotization. Okay, okay, so we start with the toluene. Okay, how do you want to do that? Toluene?
MBS.
You want to do MBS? Because you want to functionalize this carbon here by introducing bromine, right? Okay, so MBS will replace one of the hydrogen, benzylic hydrogen here. Okay, and then what do you do? Grignard again. Okay. So you form a Grignard reagent. Magnesium using ether as solvent. Okay, and then what else? CO2, carbon dioxide. Okay, very good. And then hydrogen ion. And that will give you the phenyl acetic acid. Okay. Okay, at this point, what do you want to do next?
Nitration.
Want to do nitration? We know that this group here, this is an sp3 carbon here, attached to benzene. It is an auto para director. So if you do nitration, the nitro group will go to the para position. What reagent we need for the nitration? Okay, very good. So this is like a review to all of you. Sulfuric acid and nitric acid will be, that is the reagent you need for nitration. You have to know this reagent. If you do not know the reagent in organic chemistry, you cannot do organic chemistry. Okay? So now we have this. Okay, then after you form your nitro group, what next?
H2.
Okay, you want to reduce the nitro to amino group?
Yeah.
To use hydrogen in the presence of a catalyst like palladium or platinum. Okay, or you could also use for this here, you could also use iron in dilute acid or tin chloride in dilute acid. So all of this you could use. To use this, you could also use this for the same reduction of nitro to amino. Okay? So now what we have this. Now we form our amino group. Now what do you want to do next? Okay, now you want to form the diazonium ion. That is where your diazotization comes in. For that you use nitrous acid in the presence of sulfuric acid. That gives you the diazonium ion. Of course, next to that will be your counter ion, but you don't necessarily need to write the counter ion. Okay, so you now have your diazonium salt or diazonium ion, and then what do you want to do at this point? Copper 1 oxide, right? Okay. In the presence of copper nitrate, copper 1 oxide in the presence of copper nitrate, of course in aqueous medium, and that would therefore introduce the hydroxy group into the benzene ring system. Now, folks, the only reason we are able to do this is because we know those reagents. So if anybody tells you that you could study organic chemistry without knowing reagents, that they're going to help you to study, they are just lying to you. They're wasting your time. You need to know those reagents. If you don't know them, you can't do anything. Like I keep telling you, it's almost as though you want to do arithmetic, you do not recognize 1, 2, 3, you don't know those numbers, then you cannot do arithmetic. Okay, so the first thing first is you need to know those reagents. Okay, we'll go to the next one. Okay, our follow on, can you go ahead and read this first?
Start from P bromotoluene, provide a synthetic scheme for.
Okay, thank you. Okay, so starting from P-bromotoluene, you are asked to provide the synthetic scheme for benzyl bromide. In other words, we want to go from here that is P-parabromotoluene. You want to go to here, benzyl bromide. Okay. Okay, now take a look at this, almost like the reverse of what we did before. Now take a look at this here. Okay, if we assume that this carbon here will be this carbon, all right, so that would be easy. We could very easily convert the methyl to the methylene bromide right here. Now, but now we have to lose the bromine down the road. Okay, so what does that suggest to you that you have to do? To lose the bromine from the benzene structure, yes. Ines? Diazonium ion again, exactly. So now you have to go back to diazotization again. So that is the only way you are going to be able to lose that bromine that is attached to the benzene structure. Okay? So once again, we go back to diazotization. Okay, so let us start. Start with okay, P-bromotoluene. Okay, what is the next first thing you want to do? You want to do the this part first. Okay. MBS. MBS will replace one of the benzylic hydrogen here with a bromine atom. So we got that. So this part is already done. Okay, now what do we need to do now? Grignard again, okay. Now why do you want to do Grignard? You want to form a carbon-carbon bond and then lose it? Okay, so where are you going with this? Okay, carbon dioxide. Where do you want to go with this? Okay, because this will give us this here. Now you form carbon dioxide. I mean, we form the carboxylic acid. Okay, now we've done that. Next step. Tannate chloride again. Now what do you want to do eventually? You want to form a primary amide and then? Okay, well, okay, say tannate chloride. That gives us this. Okay, Abraham, following your lead here. Now you want to add from the primary amide, ammonia. Okay. Okay, you could blame Abraham for this if this is not correct. Okay, so we'll get it. Okay, now what do we have now? We have a primary amide, right? Okay, so now you form your primary amide, so what do you want to do now? Hoffman, exactly. Now you want to do your Hoffman. Because that is how you're going to get to diazonium ion, right? Now you then do bromine or chlorine. To use either bromine or chlorine in basic medium. That will give you your Hoffman rearrangement product. Okay, now you form your amino group. Okay, now at this point, what do you want to do? Diazonium ion. Okay. Now you form your diazonium ion with nitrous acid and sulfuric acid. Okay, so you form your diazonium ion. Then you want to do use hypophosphorus acid, right? Hypophosphorus acid. That is this here. Okay, and that will remove the diazonium ion. Okay. You see the diazonium ion here is a very important reagent or reaction in organic chemistry. Okay, and so now we form our product. But without you knowing those individual reactions, this will not be possible. Okay. So once you know those individual reactions, then you will then be able to think critically to design the pathway to your product from your starting material. Okay, let us go to the next one. Okay, this here, let's see. Okay, Ines, go ahead and read this first.
The transformation below starts with mineral addition, then followed by an Aldol reaction, the condensation to ready-made.
Okay, thank you. Now, this problem here, this is a mechanistic problem in which, okay, this is for the transformation below. This transformation starts with a Michael addition reaction. They are already telling us this starts with a Michael addition reaction, and then it's followed by Aldol reaction without the condensation, without the loss of water. That is what this means, no condensation. So now they want you to provide the reaction mechanism. Okay, to help you out, let me go ahead and number this molecule so you guys can then work with me to solve this problem. Okay, let us say this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7, carbon 8, carbon 9, 10, 11, 12, 13, and carbon 14. Okay? What is the first thing you think we need to do? They have told you that you need to do a Michael addition. Keep in mind, for you to do a Michael addition, the first thing you need to do, you need to form your enolate, which is your nucleophile, right? Okay? So where are you going to form the nucleophile here? What carbon? Carbon number 3. In other words, you are going to deprotonate this carbon here. Very good. With hydroxide. Okay, so the hydroxide comes here. Abstract this proton, and you are going to therefore form your enolate right on carbon number 3. So we have this. Okay, right here, the enolate is on carbon number 3, right here. So let us go ahead and number this. Carbon 1, 2, carbon 3, 4, 5, carbon 6, carbon 7, carbon 8, 9, 10, 11, 12, 13, and 14. Now, the enolate anion will attack what carbon here? Okay, because this is a Michael addition. Okay, carbon 7, you have the alpha beta unsaturated carbonyl right here. This is the alpha position, and this is the beta position. So, this enolate here, use my red pen. The enolate here will come here, attack this here. This is your Michael reaction right here. And then the electron goes to this carbon. So you form enolate on carbon number 8. And therefore, we get this intermediate. From the enolate right here, and then we have this carbon number 7 attached to carbon number 3, okay? Okay, and then we have this here. Okay, this is carbon number 3, this is carbon number 7. Okay, so therefore we have the rest here. This will be a 5-member ring will be formed. If you look at this, you are going to form a 5-member ring. This is 1, 2, 3, 4, 5. You join in 3 and 7. Okay, so let us go ahead and number this. This is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7 right here, carbon 8, this is 9, 10, 11, now carbon 12 and 13, carbon 13 is attached to carbon 5, it's right here. And this is 12, 13, and carbon 14. Okay. Now, at this point, what is going to happen? We are going to protonate this enolate ion here, right? Because we have in solution, we have ethanol in solution. So this comes here, abstract this proton from here, and therefore we form this here. From this, okay, so now if you want to follow the numbering, you see I have carbon 1 here, 2, 3, 4, 5, 6, 7, carbon 8 now is protonated. Now 9, 10, 11, and this is 12, 13, and 14. Okay? So now that we've done that, what will be the next step? Right now we've done the Michael addition. Now they also told us that we are going to do an Aldol reaction. So what will be the next step? Okay, to form your Aldol, what are you going to do? You need to form a nucleophile. Where are you going to form the nucleophile from? Carbon number 1, exactly. So at this point, you are going to deprotonate the carbon number 1. You deprotonate carbon number 1. So that goes here. We are going to use the hydroxide again to do that. Let us take this here. So it should be obvious for us. Let us go ahead and make the CH2, and we have hydrogen here. Okay, so we deprotonate the carbon number 1 to form enolate on that. Okay. And then you form this intermediate. We have this here, this here. At this point, we now form an enolate anion on carbon number 1. Okay, so we can go ahead and number this again. Well, do we need to number this? We don't need to. Okay. So now what happens next? That enolate attacks the, okay, at carbon number 9. Okay. And this goes to oxygen, okay, and then we are almost at the end of this process. Now we have this. Okay, and right here we have this. We have this here. Carbonyl is here, and this here, and this is here. Okay. Okay, this is our carbonyl here, right here, and then finally, what do we do? Protonate that, exactly. Protonate that with from the solvent or from water, and that simply just abstract this here, goes to here, and therefore we get our final product, which is this here. Okay, so in this process here, this is just a way of ensuring that you guys know what goes on whenever chemical reaction takes place. In other words, you need to be able to account for all of those electrons. Notice what we do, we move the electron from the nucleophile to the electrophile to form new carbon-carbon bond. Okay, but the key point here, you take a very close look at your starting material, and then you take a look at the product before you can decide what kind of mechanism you are going to write by moving those electrons around. Okay, so essentially we have finished almost the whole chapter, but I do have one more reaction I want to share with you. Okay, actually 3 more reactions. What time do we have?
3 more reactions.
Oh, we got plenty of time. Okay. Let me there is a reaction we call Hoffman. Elimination. Hoffman elimination. Okay. If I have this molecule here, this is a very simple reaction. say I have this molecule. Okay? And then I react this amine, this primary amine. I have excess methyl bromide. What do you think is going to happen? Keeping in mind that you have non-bonding pair of electron on nitrogen. What do you think will happen? Okay, it will attack this, and we have excess of this. Okay, once it attacks it one time, it forms a secondary amine, then attacks again, it forms a tertiary amine. Finally, it attacks again to form a quaternary amine. So you are going to get this product. So you form a quaternary amine. These are iodide here somewhere. Now, if you take that quaternary amine, you have silver oxide to it. Add silver oxide to that. What you get is this. And then we make some room here. You get that? Now, at this point, remember here, you have iodide here. Now, this now will be replaced by hydroxide. Okay, negatively charged. Of course, the positive charge is still on nitrogen. And we still have this here. Now, if you now take this molecule and you apply heat, this hydroxide will pull one of the hydrogen here. To make it a little bit more obvious, let me take this, make this a CH2 and hydrogen here. This hydroxide here will pull this, and in so doing, the electron will come here to form a carbon-carbon double bond between this carbon and this carbon, and in so doing, you are going to release the carbon-nitrogen bond. That will break. And what do we get? We get this. Plus trimethylamine. Now, the point to be made of this, in the Hoffman elimination, what you get a terminal alkene, because if you notice here, in this reaction here, we do have a possibility of making a carbon-carbon double bond. Let us number these carbons here. Just say this is carbon 1 here, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. We have a possibility of making a new carbon-carbon bond between carbon 2 and 3, or carbon 1 and 2. But what the Hoffman elimination gives you will give you the least stable alkene. Least stable alkene will be formed. Least stable alkene is formed. And generally, that will be your terminal alkyne. Okay? So that is the usefulness of the Hoffman elimination. So if you want to specifically make a terminal alkene, or you want a reaction that will give you the less stable alkene, then you want to use the Hoffman elimination. In this case, you can see right here, okay? So that is the most important feature of the Hoffman elimination. Okay, for example, if you have this, here, we also have this. That'll be right. Okay. If you have this here, you do your excess for step 1, and then step 2, okay, now what I want to do here, let me take this out. Okay, and then you have your silver oxide, step 1, and then step 2, you apply heat. What are you going to get? You will get this product here. That is the product you are going to get, instead of getting a product in which the double bond is on the ring system. Okay? So instead of this here, you do not get this. Okay? You get the least stable alkene product. Okay. Okay, so anyway, so that is the beauty of the Hoffman elimination. It just allows you to form the terminal alkene, and generally will be the least stable alkene in the reaction. And I told you a couple more reactions. Okay, now the last 2 reactions, but these are, you don't need to know this for the 4th exam. I know you guys are worrying about the exam. Now this here, just for your information. No, you don't need to know this but you need to know this if you want to do your MCAT and all that kind of exam. Step gross polymerization. Okay. Remember, you guys, how many of you use a nylon socks? Okay. You use a nylon fabric. You use polyester fabric. Okay. Now, if you take this molecule here, okay, that's a diacid chloride, and you take take this amine, and then you take this diacid chloride, these two will react. Okay, this will react with this now electrophilic acid substitution and reaction, nucleophilic acid substitution reaction. What do you get? You get this. Now this reaction could continue because on this side we see have the amine here. Now this reaction to continue until you get what we call a polymer, a very long chain, amide chain. This will be eventually give you have another diamine here. So now you get this. And this process will continue. This process will continue until you get what we call here, if you look at this, a chain of what we call polyamide. Okay? This polyamide, this is your nylon. This particular nylon is called nylon 66. And that is what you use for your nylon socks and for your pantyhose, all of those nylon fabric. So starting from very simple molecule, now to actually make a very important industrial material. So on this note, we have come to the end of the semester. Okay, and I will see you for the seniors. I will see you on Wednesday, and for the rest of you, I will see you on Thursday. Okay, so enjoy the rest of your evening.
Yeah.